All right, this is the 2004 free response question for the AP exam. It is an essay question, so most likely from the second half of the test when you are not allowed to use a calculator, and you must account for things based on what you know about chemistry as a science. If you have not done this question on your own, please stop or pause this video. Come back after you have done it. I will go over where you can get points, and we'll see how you do. You don't need to get a perfect score. You don't have to have the answer exactly the way I do. But if you have 3, or if you have 4 of the possible 8 points for this question, I'm assuming it's 8 points, I don't know off the top of my head, that is doing very well. So stop this video, pause it, answer the question, and then come back and watch me go through everything. So I'll take a short pause. All right, so coming up on this question, there's no data table, so nothing to look over really quickly. All we got to do is just read the question. What does it say? Use appropriate chemical principles to account for each of the following observations. In each part, your response must list specific information about both substances. That's always a good statement to have. They won't always tell you that. But in order to get points, usually on a free response question, you have to talk about the 2 things that they give you. So don't talk about one and assume the other one, or assume they'll know that the other one is the opposite. You have to state both in order to get the points. Okay, so at 25 degrees Celsius and 1 atmosphere, fluorine is a gas, whereas iodine is a solid. So why is that? All right, so what do we know about fluorine and iodine? You might want to do a Lewis structure really quickly. And if you do, you find fluorine, single bond, iodine, single bond. Okay, that doesn't help us at all. What else do we know about fluorine and iodine? Well, fluorine is really, really small. Fluorine has a total of 18 electrons. Iodine has a total of 106. That's a lot of electrons. So that's a big difference. Okay, so it must have something to do with that. Well, what do we know about what do we know about these states of matter? States of matter are relative to the intermolecular forces for covalent compounds. The stronger those intermolecular forces, the less chaotic that state of matter. So a solid must have really strong intermolecular forces, or relatively strong intermolecular forces, and a gas must have relatively weak ones. So what intermolecular forces are present here? Well, this is nonpolar, so that's London dispersion forces. Iodine is also London dispersion forces. And now you got to think, what do I know about London dispersion forces? They increase with increasing number of electrons. So now I got to tell this to my graders so that they know I know about London dispersion forces. So let's talk about both. Fluorine and iodine exhibit London dispersion forces, which increase with increasing number of electrons. Iodine with 106 electrons is more, here's the buzzword for this unit, polarizable. I think I missed that. Polarizable than, that should be an F. Always have a good eraser. Fluorine with 18 electrons. Whew. That word polarizable or polarizability is a huge lifesaver, because otherwise you would have to talk about how there's an unequal distribution on both sides of the atom, and therefore iodine has a more positive and negative charge than fluorine at any given moment. Oh, it's a mess. So instead, we use the word polarizability. That's a big one. If there was one word you could get from this unit, polarizability, and knowing when to use it, when you have 2 things that exhibit London dispersion forces, that's going to be a big lifesaver. All right, so as far as points go for this question is worth 2 possible points. 1 point for identifying that both exhibit London dispersion forces, and then indicating that iodine is more polarizable than fluorine. All right, number next is invisible apparently. There we go. Number next. The melting point of sodium fluoride is 993 degrees Celsius, whereas the melting point of cesium chloride is 645 degrees Celsius. So why is that? So what do we know about these two? Well, they're both ionic, and ionic bonds are held together by a Coulombic force, which is proportional to the charge of one ion times the charge of the second divided by the distance between them. So maybe it's the two charges. Fluorine is a plus one, or sorry, sodium is a plus one. What? Pause. What a mess. Okay. It's a plus one. Fluorine's a minus one. Okay. This is a plus one. That's a minus. Oh, that's not good. Okay, so it's not going to be these values that are different. Those are going to be the same. R is the distance between the two. So I have sodium, which is pretty small. Near the top of the periodic table, only has three shells. I have fluorine, has two valence shells. Cesium's got six. Woo! Period 6, so it's got 6 shells. And chlorine has 3 shells. So that's a pretty sizable difference. So it's this value that's changing. So rather than get rid of this, I'm just going to explain this equation, but I'm going to move it off to the side. Which granted on your test you might not be able to do because you don't have a smartboard, but you can write around or near what you're doing and then circle or square off your answer so the grader knows to look at that particular thing. So I've got to describe this. The strength, let's talk about both first. Erase. Both sodium fluoride and cesium chloride are ionic compounds whose electrostatic force is proportional to Q1, Q2 over R squared. The size of the cesium ion is significantly significant. I can't fit you. Same sauce. Significantly larger than the sodium ion. And the fluoride ion is smaller than the chloride ion. Therefore, that is a screwed up therefore. Erase. Therefore, the R squared value for sodium fluoride is smaller than for, I have to scroll down a little bit, cesium chloride, and therefore is a stronger bond which must be overcome to melt. Whew. A lot of writing there. Lots of thought process between it. But this formula, guys, will get you out of a lot of sticky situations. Both are ionic, so if I didn't know about that formula, I would have a harder time explaining it. I'd have to talk about the bond length, and that would be one way to go about it. Well, the bond length is closer together. But bond length has a lot more to do with covalent compounds than it does with ionic compounds. In ionic compounds, it's the Coulombic force, it's the electrostatic force holding those two ions together. So let's see how we do. Point-wise, question I believe is also worth 2 points. Pointing out that both are ionic in itself was 1 point, because it says make sure you talk about both of them. So I talked about both, they're both ionic. And then 1 point for indicating the strength is determined by the distance. So talking about this R squared value does that. Talking about the bond length would do that. I hesitate to let you get away with saying bond length because that is more prevalent or more useful when it comes to covalent compounds. Stick to electrostatic forces. They're ions. What's holding them together? Those charges. All right? The charges and then the distance between the nuclei and the amount of shielding that nuclei has from its electrons of other ions. Okay, so stick to the correct vernacular. All right, another question with some overlap. Here we go. The shape of the iodine tetrachloride anion is square planar, whereas the shape of the boron tetrafluoride ion is tetrahedral. Okay, so now we got to do some drawing here. What do we got? I have iodine tetrachloride. So that's, let's see, I count up some valence electrons. I have 7 from iodine, 4 times 7 from chlorine, and then the negative means that there's 1 extra electron. So this is 5 times 7, that's 35, plus 1 is 36 valence electrons. That means that I have 18 pairs to play with. So put my chlorines around it in no particular order, left, right, upside down, don't care. It uses up 4, I'm down to 14. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. I'm down to 2 left. Any extras go on the central atom. Can iodine have an expanded octet? Yes, it is after period 3. So that's okay. Okay, so there's my iodine anion, or iodine tetrachloride anion. What do we got over here? I got boron with 3 valence electrons, and I have 4 times 7 plus 1 more for the charge. So I have really 4 times 8. I've got 32 valence electrons, so that means I've got 16 pairs. So boron in the center, least electronegative in the center, fluorines around it in no particular order. Let's see, I've used up 4. I'm down to 12. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. All right. My Lewis structures are good with the exception that they are both ions. So let's put those in brackets because they have a charge. That's negative. That's negative. All right. So now I've got 2 different Lewis structures here. What do I got? I've got something with 1, 2, 3, 4, 5, 6 regions of electron density, so it needs 6 letters for its hybridization. Goes SP, goes SP3, that takes 4, and then the S will be D, so D2. 6 letters for my hybridization. SP3, D2, its electron geometry is octahedral, but with 2 valence, or with 2 lone pairs, they're going to want to space out as much as possible, so they'll be on the top and the bottom, or the left and the right. But no matter how you slice it, this is going to be square planar. All right, so that's square planar because it's D2SP hybridized with 2 lone pairs. And therefore, it's square planar. One of those things you just have to have memorized. Figure out the hybridization is pretty easy. Count the regions of electron density. So this has 4. You need a letter for each one. S's only have 1 orbital. P's have up to 3 orbitals. So sp3 hybridized, anything that's sp3 hybridized is tetrahedral when it comes to its electron geometry. Molecular geometry, no lone pairs. With no lone pairs, it's going to be the same thing. So its molecular geometry is tetrahedral. So now I just need to tell my grader this. Iodine tetrachloride is sp3d2 hybridized with 2 lone pairs. Therefore, it is square planar. Bf4 minus is sp3 hybridized with no lone pairs, therefore tetrahedral. Oh, I can't spell today, I can't work. What is wrong with me? Not only that, it's a freaking problem, Adam. Come on. Okay, let's see how we did. This question was worth 2 points, and it was fairly simple. Pointing out that iodine tetrachloride had 2 lone pairs, got you 1 point, and that boron tetrafluoride had no lone pairs, netted you the other. The talk of hybridization would just be your explanation for why those particular shapes exist, but this question wasn't looking for all of that. It is possible that you could have gotten those points from just the structures. However, you're going to want to point out the key difference between them in writing somehow. If you do not, you are not likely to get all of those points. You would maybe get 1 or 2 of those points, or 1 of those points rather than both of them. You do need to, in an essay question, at least use some words or vernacular. All right, the last question deals with solubility. Ammonia is very soluble in water, whereas phosphine, pH 3, is only moderately soluble in water. Last one. Ammonia is very soluble in water, whereas phosphine is not, or is moderately soluble. All right, so maybe right off the bat you might go, okay, so ammonia 5 plus 3 times 1, so I have 8 valence electrons to play with. Nitrogen to each one of these hydrogens, that uses up, so that means I only have 4 pairs. So that uses up 3 of them, I'm down to 1, goes like that. Hopefully, at this point in your career, you know what ammonia looks like. You might do the same thing with phosphine, but since ammonia and since nitrogen and phosphorus are in the same family, it's going to be the same structure. Okay, so it's not a Lewis structure difference. Sad face, because that would have been easy. So it must be something different. What's going on here? What type of intermolecular forces are at work here? So if I have just these in solution, if I have just these not in solution, if I have a pure sample of ammonia and I have a pure sample of phosphine, what intermolecular forces am I going to have? Well, for phosphine, they're both polar, right? That lone pair is a region of electron density that's much higher than anything else. It's going to push all those electrons. It's going to pull on all those electrons greater. So we have an unequal dipole. We have a dipole moment. So both of these are polar. So dipole is the London dispersion force for both of them. However, with ammonia, you can form hydrogen bonds, which, remember, is not the bound hydrogens. It's not the bond between nitrogen and hydrogen. It's the attraction of a neighboring hydrogen bound to another nitrogen. So ammonia can exhibit hydrogen bonds. You know what else can exhibit hydrogen bonds? Our good buddy water. Because hydrogen bond exists between a hydrogen that's bound to a nitrogen, oxygen, and fluorine, and a neighboring nitrogen, oxygen, or fluorine. So that is going to contribute to ammonia's solubility. So ammonia exhibits hydrogen bonds. Which it can use, atoms don't use things, which can, not it, ooh, that was a weird jump, which can allow it to attract or be attracted. That's an attempt at the word attract. Water. Phosphorus or phosphine does not have hydrogen bonds and therefore can only attract water by dipole forces. Okay, for this question, you got 2 possible points. 1.4, pointing out the 2 types of intermolecular forces, or the strongest 2 intermolecular forces present for both, and then relating it to how it reacts with water. That was the second point. So, just talking about the 2 forces involved in itself was 1 point. So this little diagram we did off to the side, that might have gotten us 1 of the 2 possible points. But we need to talk about how it's reacting with water because it is talking about solubility. So, in total, this question is worth, I believe, 8 possible points. 2, 4, 6, and then 8. Remember, getting 4 out of the 8 total points, it puts you well on track to getting that 3, 4, or 5.